All right, let's talk speed.
Oh, yeah.
I bet you're like me, always looking for that extra edge to make your code run faster.
Always.
Well, today we're diving deep into cache and memory optimization. And trust me, this stuff can make a huge difference. We've got this awesome blog post from Algo Academy as our guide, and they're going to walk us through some seriously clever techniques.
You know, it's funny. We spend all this time fine-tuning our algorithms, but sometimes the real bottleneck is how our code interacts with the hardware itself. That's where cache and memory optimization come in.
Yeah, it's like having a race car with a clogged fuel line.
Mm,
All that potential power, but it just can't deliver.
right.
So let's start with the basics. What exactly is a cache, and why should we care about it so much?
Think of a cache as a high-speed staging area for your data located right next to your processor. It holds the stuff your program is most likely to need next so it can be accessed super quickly. Without the cache, every time your code needs a piece of data, it would have to fetch it from the main memory, which is like taking a long detour.
Okay, so the cache is like having a shortcut to the information your code needs most often.
Yeah.
But I've heard there are all sorts of different caches. How do they all fit together?
It's like a hierarchy, starting with the super fast but tiny registers inside the CPU. Then you've got different levels of CPU caches, each getting progressively larger but a bit slower. And then we move down to the main memory RAM, followed by SSDs, and finally the hard drives. Each level holds more data, but accessing it takes longer.
Whoa. It's like a pyramid of memory with the fastest stuff at the top and the slowest at the bottom. So how do we make sure our code is using the right level at the right time?
That's where understanding the principles of temporal locality and spatial locality comes in. Temporal locality means if a piece of data was used recently, it's likely to be used again soon. So keeping it in a fast cache makes sense. Spatial locality means that data stored close together is often accessed together.
So it's like grabbing all the ingredients for a recipe at once instead of making multiple trips to the fridge.
Exactly. By organizing our data cleverly, we can take advantage of these principles and make our code run much faster.
Okay, so we've got this hierarchy of memory, and we want to make sure our code is using the fastest levels as much as possible.
Right.
Let's dive into some of the specific techniques for optimization. What are some of the things we can actually DO to make our code more cache-friendly?
One technique that's often overlooked is data alignment and padding.
Oh, yeah.
You might think that how you arrange data within a structure doesn't matter much, but it can have a big impact on performance. Imagine cache lines as containers for chunks of data. If your data is aligned properly, it fits neatly within those containers. But if it's misaligned, you can end up with wasted space and slower access times.
So it's like packing a suitcase efficiently. You want to make sure everything fits in nicely without wasting space.
Exactly. They even had a C++ example in the blog post to illustrate this. They showed how a poorly organized structure could lead to performance issues just because the data wasn't aligned properly. But by rearranging the data, they were able to fit everything nicely into the cache lines, which led to a significant speed boost.
That's pretty cool. It seems like something that's easy to overlook but could make a real difference.
Uh-huh.
What about this loop tiling technique? That sounds intriguing.
Loop tiling is especially powerful when you're dealing with large data sets and nested loops like in matrix multiplication.
Hmm.
The basic idea is to break down the problem into smaller chunks that fit better in the cache. Imagine you're painting a huge wall. Instead of trying to cover the whole thing at once, you might divide it into sections and work on one section at a time. That way you can keep all your tools and paint close at hand without having to constantly go back and forth for more supplies.
So instead of processing the entire matrix at once, you break it down into smaller tiles that can be handled more efficiently by the cache.
Exactly. They showed how transforming a regular matrix multiplication loop into a tiled version led to a massive performance improvement. It's all about maximizing cache hits and minimizing those slow trips to main memory.
Okay, that makes sense. Now, they also mentioned something called prefetching. Is that about trying to predict what data your code will need next?
That's a great way to put it. Prefetching is like having a mind-reading assistant who anticipates your next move and starts preparing things in advance. It involves loading data into the cache before it's actually needed, either automatically by the hardware or through specific instructions in your code.
That sounds pretty awesome, but also a bit risky.
Yeah.
What if you prefetch the wrong data? Wouldn't that just clog up the cache and make things slower?
It's a balancing act for sure. Prefetching too much of the wrong data can be counterproductive.
Right.
But when done right, it can dramatically improve performance. The key is to understand your code's access patterns and use prefetching strategically. They even provided a C++ example showing how to use special instructions to prefetch data ahead of time.
So far, we've been talking a lot about optimizing cache usage.
Right.
But what about memory management itself? How does that fit into the picture?
Memory management. It's like keeping your workshop tidy.
Okay.
If you're not careful about how you allocate and deallocate memory, you can end up with fragmentation leaks and all sorts of performance bottlenecks. The Algocademy post highlighted some key strategies for effective memory management, and I think they'll be particularly helpful for our listener.
I'm all ears. I know memory leaks can be a real pain. It's like a slow drip that eventually floods your entire program.
Exactly. And sometimes it can be hard to track down the source of the leak. That's why it's so important to have good memory management practices in place from the start. They talked about memory pools, which are like pre-allocating chunks of memory for specific purposes.
So instead of constantly requesting and releasing small bits of memory from the operating system, you have these dedicated pools for different types of data.
You got it. It's like having designated containers for your tools material and finished products. It keeps everything organized and avoids the overhead of constantly searching for the right space.
I like that analogy.
Yeah.
Makes a lot of sense. What other memory management techniques did they mention?
Well, they talked about smart pointers, which are like self-cleaning containers. They automatically deallocate memory when it's no longer needed, preventing those pesky memory leaks we were just talking about.
So they take care of the cleanup for you. That sounds pretty handy.
It really is. C++ has std.uniqueftr and std.sharedptr, which are great examples of smart pointers. Then there's memory mapped files, which is a bit more low level, but can be super efficient for working with large files.
Memory mapped files. I'm not too familiar with that one.
It's a technique that lets you treat a file on disk as if it were part of your program's memory. The operating system handles the loading and caching of data as needed, so you don't have to worry about manually reading and writing chunks of data.
So it's like having direct access to the file without having to go through all the usual file BIOS steps.
That's the idea. They provided a C example using the ummap function. It can be a bit more complex to set up, but it can be a real performance booster for certain applications.
It seems like there's a whole toolbox of techniques for managing memory effectively. It's not just about writing efficient code, but also about how you handle the underlying memory resources.
Exactly, and it's all connected. Choosing the right memory management techniques can have a big impact on how well your code can utilize the cache and vice versa.
This is getting pretty deep. I'm starting to see how all these pieces fit together. We've talked about the memory hierarchy cache optimization and now memory management. What about the data structures and algorithms we use? Do those have a big impact on performance as well?
Absolutely. They can make or break your optimization efforts. Even if you're using all the right cache and memory management techniques, if you're using a data structure that's not well suited for the task at hand, you're going to run into performance issues.
The Algocademy article mentioned cache-friendly data structures. What exactly does that mean?
It means choosing data structures that are designed to work well with the way caches operate. For example, array-based structures like C++ std.vector are often a good choice because they store elements contiguously in memory. This plays nicely with the principle of spatial locality we talked about earlier, since accessing one element often means you'll also need to access nearby elements.
So it's not just about picking the right data structure, but also about how the data is organized within that structure.
Precisely. They even talked about transforming arrays of structures, AOS, into structures of arrays, so A, to improve cache utilization. They used a particle structure as an example. By grouping related data together, you can make it much easier for the cache to fetch the information it needs.
So it's like organizing your workshop so that all the tools for a particular task are grouped together.
That's a great analogy. The goal is to make sure the data your code needs is stored in a way that minimizes cache misses and maximizes performance.
This is fascinating stuff. I'm starting to see how much thought goes into optimizing code at this level.
And we've only just scratched the surface. There's a whole world of cache-aware algorithms that are specifically designed to take advantage of caching mechanisms.
I've heard of cache-oblivious algorithms too. How do those work?
Cache-oblivious algorithms are pretty clever. They're designed to work well across different cache architectures without needing to know the specifics of the cache they're running on. It's like having a universal tool that works equally well in any workshop. They gave a cache-oblivious matrix multiplication algorithm as an example.
That sounds pretty powerful.
Yeah.
And then there are cache-conscious algorithms which are tuned for specific cache architectures, right?
Exactly. Like the cache-conscious quicksort they mentioned, which uses insertion sort for small subarrays that fit entirely in the cache. These specialized algorithms can be very effective, but they require more in-depth knowledge of the target hardware.
So there's a whole spectrum of approaches, from the general purpose to the highly specialized. It seems like the key is to understand your specific needs and choose the right tool for the job.
You got it. And speaking of choosing the right tool, how do we know if our optimizations are actually working? How do we measure and profile performance? That's what we'll be diving into next.
All right, I'm really curious to see how these optimization techniques play out in the real world. The Algo Academy post mentioned some pretty impressive examples from tech giants like Google and Facebook.
It's amazing to see how these seemingly abstract concepts translate into real-world performance gains for companies that handle massive amounts of data and traffic.
Let's start with Google's Bigtable, a distributed storage system that handles, well, big data.
Bigtable is a fascinating example of how a multi-level caching strategy can be used to optimize data access. It's not just one cache, but a whole hierarchy of caches working together to ensure that data is available as quickly as possible.
They mentioned a tablet server cache that stores frequently accessed data in memory on each server. It's like having a local stash of the most important information.
Exactly. It's the first line of defense, providing quick access to the data that's most in demand. But it doesn't stop there. They also have a block cache that caches as stable blocks, which are essentially chunks of data stored on disk.
So they're caching data at different levels of granularity, from individual data entries to larger blocks.
That's right. By caching data at multiple levels, they're maximizing the chances of finding what they need without having to go all the way to disk, which can be a real performance killer. And to further reduce unnecessary disk reads, they use something called Bloom filters.
Balloon filters, refresh my memory on those.
Think of Bloom filters as a super fast maybe checker. They can quickly tell you if a piece of data is definitely not in a set, so before even checking the cache or disk, they can quickly eliminate requests for non-existent data, saving precious time and resources.
Ah, that makes sense. It's like a pre-filter that helps them avoid dead ends.
Precisely. And this multi-tiered caching approach, combined with clever techniques like Bloom filters, is a key part of what makes Bigtable so efficient at handling massive amounts of data.
It's impressive how much thought and engineering goes into optimizing every step of the data retrieval process.
Absolutely. And it's not just Google that's pushing the boundaries of caching. Facebook's use of Memcached is another great example of how distributed caching can be used to achieve incredible performance at scale.
Memcache is a popular open-source caching system, but I imagine Facebook is using it in some pretty sophisticated ways.
They've taken it to a whole new level. They use consistent hashing to distribute cache keys across a vast number of servers, ensuring that data is spread evenly and requests are handled efficiently. And to squeeze out even more performance, they use the UDP protocol for GET operations.
UDP is known for being faster than TCP, but it's also less reliable. Isn't that a risk?
It is a trade-off, but in a system as large as Facebook's, even a small reduction in latency can make a big difference. They've designed their system to handle the occasional UDP packet loss without impacting overall performance. They've also implemented a lease mechanism to prevent what they call thundering herds.
Thundering herds. That sounds a bit dramatic.
Imagine a scenario where a popular piece of data suddenly expires from the cache. Thousands of requests might simultaneously hit the database, overwhelming it and causing performance issues.
Ah, so it's like a stampede of requests all trying to get to the same data at the same time.
Exactly. The lease mechanism acts like a gatekeeper, allowing only one request to fetch the missing data while others wait. It's a clever way to ensure a more controlled and orderly process.
So they're not just distributing the cache, they're also managing the flow of requests to prevent those sudden bursts of traffic that can bring the whole system down.
Precisely. These optimizations allow Facebook to handle billions of cache operations per second, which is just mind-boggling. It really showcases the power of distributed caching at a truly massive scale.
These examples from Google and Facebook are really impressive. But it seems like caching is also crucial at the operating system level. The article highlighted the Linux kernel page cache. What's that all about?
The page cache is essentially a giant cache that the Linux kernel uses to optimize file system operations. It caches recently accessed disk blocks in memory, so the next time they're needed, they can be accessed much faster. It's like having a shortcut to your most frequently used files.
They mentioned read ahead, which sounds like the prefetching we were talking about earlier, but for file access.
I got it. The page cache anticipates future file accesses and proactively loads data into memory, speeding up subsequent reads. And it also uses write back to improve efficiency.
So instead of immediately writing changes to disk, they're buffered in memory and written later in batches.
That's right. It reduces the overhead of disk operations and can significantly improve performance.
They also emphasize that the Linux page cache is a unified cache, meaning it's used for both file I/O and anonymous memory mappings.
It's a clever way to share cache data across different parts of the system, further improving efficiency. It's like having a central library that everyone can access rather than everyone having their own separate collections.
It's amazing how caching is woven into so many layers of computing, from the CPU to distributed systems to the operating system itself.
It really highlights the importance of optimizing data access and minimizing those costly trips to slower storage. And as technology advances, new trends are emerging that could further revolutionize cache and memory optimization.
That's what I'm really curious about. The Algo Academy post hinted at some of these future trends. What's on the horizon for cache and memory optimization?
One of the most exciting developments is the rise of non-volatile memory, or NVM technologies like Intel's Optane are blurring the lines between memory and storage, offering new possibilities for persistent caching and high-performance data management.
So it's like having memory that's as fast as RAM, but can also retain data even when the power is off.
Exactly. Imagine the possibilities. We could have systems that boot up instantly and applications that can access vast amounts of data with lightning speed. It could fundamentally change how we design and optimize systems.
That's pretty mind-blowing. What other trends are on the horizon?
Well, there's the potential of machine learning for cache prediction. Imagine using AI to predict what data will be needed next and prefetch it with even greater accuracy.
It's like taking prefetching to a whole new level. Instead of relying on simple heuristics, we could have intelligent systems that learn from past behavior and anticipate our needs.
Precisely. And then there's the wild card of quantum computing. It's still in its early stages, but quantum computing has the potential to revolutionize many fields, including cache and memory optimization. Quantum algorithms could enable us to solve certain optimization problems exponentially faster than classical computers.
Quantum computing always sounds so futuristic. It's hard to even imagine what kinds of breakthroughs it might enable.
It's definitely a field to watch closely. And let's not forget about edge computing, which is all about bringing computation closer to the source of data.
Edge computing is becoming more and more important as we rely more on devices and sensors that generate massive amounts of data.
Right. And it presents new challenges and opportunities for caching and data management. As data is generated and processed at the edge, new caching strategies will be needed to optimize performance in these distributed environments.
It seems like the future of cache and memory optimization is full of exciting possibilities.
It certainly is. But with all these amazing advances, it's important to remember that. It's important to remember that cache and memory optimization, it isn't a one-size-fits-all solution.
Yeah, that's a good point. We've covered so many different techniques and approaches. It can be a bit overwhelming.
It is. It's about finding the right balance for your specific needs and using profiling to make informed decisions.
So it's not just about blindly applying the fastest algorithm or data structure.
Exactly. Sometimes a simpler approach might be more efficient overall. It's all about understanding the trade-offs and choosing the best solution for your particular problem.
The Algo Academy post really emphasized that cache and memory optimization is an ongoing process. It's not something you do once and forget about.
Absolutely, as your code base evolves, new bottlenecks might emerge or hardware architectures might change, requiring you to revisit and refine your optimization strategies.
It's like a constant dance between code hardware and performance.
That's a great way to put it. And the most important takeaway, I think, is to stay curious.
Yeah, curiosity is key. Always be on the lookout for new techniques, tools, and trends that can help you write faster, more efficient code.
This field is constantly evolving, so staying up to date and being willing to experiment are crucial for staying ahead of the curve.
Well, this deep dive has definitely sparked my curiosity. I'm already thinking about how I can apply some of these techniques to my own projects.
Me too. It's been a fascinating exploration of the intricate world of cache and memory optimization.
From understanding the memory hierarchy to mastering techniques like loop tiling and prefetching, we've gained a whole new appreciation for the art of writing high-performance code.
And by examining real-world examples from tech giants and considering emerging trends, we've glimpsed the future of this ever-evolving field.
So to all our listeners out there, remember, the key to unlocking your code's full potential lies in understanding how it interacts with the underlying hardware. Embrace the challenge, stay curious, and keep pushing the boundaries of performance.
And on that note, we'll leave you with a provocative question to ponder. What if we could design systems where memory was so fast and efficient that caching became almost irrelevant? What would that world look like?
That's a thought-provoking question indeed.
Well,
Thanks for joining us on this deep dive into the fascinating world of cache and memory optimization. Until next time, happy coding.